This module introduces basic cryptography and public key infrastructure. At the end of the module, you will understand and explain, be able to explain to your peers and perhaps your boss the way a public key infrastructure really functions. We'll talk about basic cryptography, the difference between symmetrical and asymmetrical encryption, and the fundamentals of a PKI, or public key infrastructure. Some vocabulary. We use the term encryption. Encryption is a process of turning a plain text message, also known as plain text, into random data streams that looks like a meaningless or random message, also called ciphertext. Reversing that process, turning the ciphertext back into readable plain text, is called decryption. The rules we follow to transform from plain text to a ciphertext are called an encryption algorithm or a cipher. This is a mathematical function that provides step-by-step directions for how the computer or a person would perform that transformation. A key is an item, a piece of data, known only to appropriate people that is mixed in with the plain text in the process of transforming it into ciphertext. You can only transform from ciphertext back to plain text if you have the appropriate key. So key management becomes vital. Symmetrical encryption uses the same algorithm to encrypt and to decrypt, and uses the same key to encrypt and decrypt. If Alice wishes to encrypt the message and send it to Bob, Alice uses a symmetrical algorithm and her key to encrypt plain text into ciphertext. Bob then uses the same key and the same cipher to decrypt the message. So distributing the key securely from Alice to Bob is a challenge. Asymmetrical encryption works differently. Here we have a pair of mathematically related keys. One key is used to encrypt and then cannot be used to decrypt. The second mathematically related key is used to decrypt message encrypted with the first. In practice, we keep one of these keys private and label it the private key. The other key is labeled public and is distributed to anyone. How do we use this? We call this application public key cryptography. We use an asymmetric encryption algorithm and a public-private key pair in the following manner. If Alice wishes to encrypt something for Bob so that only Bob may read it, she obtains a copy of Bob's public key and encrypts the message with that key. Then only Bob, because only Bob possesses Bob's private key, can decrypt that message. Therefore, one of our security goals of confidentiality is guaranteed. But how does Bob know who the message came from? If Alice encrypts a message with her private key and transmits it to Bob, then Bob can use Alice's public key, which anyone can obtain, to decrypt the message. Since anyone can obtain Alice's public key, there is no guarantee of privacy. But since only Alice has her private key, only she can encrypt with it. Therefore, Bob knows the message came from her. I can combine these two properties for a further goal. If Alice wishes to send a message to Bob so that only Bob can decrypt it, but also provide a guarantee that Alice and only Alice sent the message, she would do the following. She would encrypt the plain text with Bob's public key. Now only Bob can decrypt it with his private key. Then she would encrypt the message again using her private key. Bob can decrypt that with Alice's public key. Anyone can do this, and anyone can tell that Alice signed the message. Bob can further then decrypt the inner message with his private key, revealing the secret or ciphertext. By utilizing these properties of public and private key pairs, we can gain a couple of interesting benefits. First, when Alice encrypts a message with her private key, only she has the private key. Only she can encrypt with it. Anyone can decrypt it with her public key. Alice is effectively signing the message that she encrypts with her public key. Correction, with her private key. This is called a digital signature. Further, because only Alice can encrypt with her private key, she cannot at some later point claim to have not sent or signed a message encrypted with it. So we have gained the property of non-repudiation. A message encrypted with Alice's private key must have come from Alice and only Alice. Therefore, she cannot say that she did not sign it or send it. Non-repudiation is a term for the property I've just described, where someone cannot claim to have not done something they actually did. This term flows from the law. Non means no, repudiation means to deny, so non-repudiation means no ability to deny. So, if we're using an asymmetrical cipher, the distribution of the public keys becomes a critical resource. How do I know whose public key I have in my hand? We answer this question of the identity of the public key through a public key infrastructure. The public key infrastructure relies on three critical logical entities called a registration authority, the certificate authority, and the validation authority. The role of the registration authority is to investigate and to determine that an individual who claims to be Alice actually is Alice. The registration authority will follow a set of public rules to determine what Alice has to do to prove her identity. Once the registration authority is satisfied as to Alice's identity, he passes function to the certificate authority. The certificate authority will take a special message called the certificate signing request that has Alice's name paired with other information and will digitally sign it based on instruction from the registration authority. The digital signature indicates that the registration authority is satisfied that Alice has proven her identity. The certificate authority signs certificate requests with his private key. So those certificates can be validated by the certificate authority's public key. A signed digital certificate request becomes a digital certificate. The digital certificate signed by the certificate authority is passed to the validation authority, who stores it and distributes it and validates it upon request. In practice, these three entities are often combined into a commercial or government body called colloquially the certificate authority. How does this really work? Alice or Bob would generate a public-private key pair, and then using that public-private key pair, take the public key and insert it in a message paired with their identity. They transmit that message to the registration authority. The registration authority performs their investigation, validates the identity, and when they're satisfied, they transmit that message to the certificate authority, who signs it with the certificate authority's private key. That signed request becomes a digital certificate, and it is provided both to the original requester and the validation authority. Now, when the original requester wishes to communicate securely with a third party, they can encrypt the message with their private key and transmit it to the third party. If the third party does not already have a copy of the individual's public key, they request it from the validation authority, and they can validate the signature of the message. This is a public key infrastructure. In the United Arab Emirates, the Emirates ID Authority is positioned to provide all of these functions. Every Emirates resident carries an Emirates ID card which contains a digital certificate. One of the hardest parts of managing the security of mobile applications is determining and managing the identity of the users. Emirates ID has solved the hardest part of this problem for us and for government users. Thank you.